Let us start our discussion on calculation of AC quantities today. So before starting this discussion, let me tell you what's the difference between calculation of AC quantities and DC quantities. For DC sources, mostly for DC voltage sources or for DC current sources, these are having only magnitudes. But AC sources should have its magnitude along with some phase angle. So whenever phase angle is involved in any circuit calculation, then the calculation becomes a bit complex. Say you can easily add two DC quantities, but addition of two AC quantities involving some phase angle is a bit difficult compared to calculation of DC quantities. So today we'll be discussing about calculation of AC quantities, how to perform mathematical operation, basic mathematical operations such as addition, subtraction, division, and multiplication of AC quantities involving phase angles. Now the question comes, why calculation of AC quantities is needed? See, you all know there are two types of two types of sources mainly. One is AC source, another is DC source. So for our domestic applications, all the appliances are run by AC sources. So very frequently we need to analyze electric circuits with AC sources. So until and unless we know how to calculate AC quantities, we can't apply that method or that concept to solve AC circuits. So in order to solve AC circuits, in order to get voltage values or current values of any AC circuit, we need to know how to calculate AC quantities. That is why we'll be studying today calculation of AC quantities. So our main objective is to understand calculation of AC quantity so that we can apply that concept to solve AC networks. So why shall we study this topic? Why calculation of AC quantities? What are the topics to be covered today? Why calculation of AC quantities needed? Different representation of AC quantities such as in polar form or in rectangular form. Different mathematical operations such as addition, subtraction, division, multiplication of AC quantities, and some basic examples. So this will be covered, we'll be covering in today's lesson. So why calculation of AC quantities is needed? As I said, most of the electric circuits involve AC sources. For domestic applications, all the appliances are run by AC sources. So calculation of AC quantities must be known to us in order to solve AC networks. Now, AC sources involve magnitude as well as phase angle. Unlike DC sources, DC sources only have magnitude. So calculation of DC sources is much easier, but calculation of AC sources involving some phase angle is a bit different. For example, suppose I have asked you to add 5 plus 2. It simply will be 7. But if I ask you to add 5 angle 2 degree plus 2 angle 8 degree, what should be its answer? This we need to know, and after completion of this lesson you will be able to calculate this value. So our objective is to calculate AC quantities, that means having magnitude and phase angle both. So for that we'll be discussing today's topic. Due to having phase angle, calculation of AC quantities is more complex compared to DC quantities. To analyze electric network with AC sources, calculation procedure of AC quantities need to be known, as I said. So these are the necessity of, these are the point for which we must study calculation of AC quantities. Now, a DC quantity should be represented graphically like this. Suppose this is 8. So this, suppose this is voltage axis and this is time axis. So see, this voltage is in parallel with reference axis. So V can be written as simply 8. Always phase angle will be 0 degree as it is parallel to X axis or reference axis. So V equals to 8 volt is, this we all are familiar with, but as shown here, an AC quantity would be like this. Suppose this is angle 30 degree and this is having a magnitude of 10. Then this should be represented by 10, that is magnitude, angle 30 degree. So AC quantities should have some magnitude along with its angle. Okay, so here we have represented an AC quantity by this, with this one, by this phasor. This is denoted by Z. Now this Z phasor is having one magnitude, that is R, and it is making an angle of phi, with the reference. So what can we write? Z equals to R angle phi. This form of representation is known as polar form. Okay, so we can represent AC quantities in 3 ways: in polar form, in rectangular form. Another form is not been mentioned here, that is known as exponential form. For our AC circuit calculations, if we know polar form and rectangular form well, we can make the calculations. That is why I skipped intentionally that exponential form, part. Exponential form, which is a e to the power j theta. This is exponential form. I've skipped this part. Okay. Now, magnitude along with angle is known as polar form of representation. And if an AC quantity is represented by x plus jy, then it will be known as rectangular form of representation. For example, suppose this is your AC quantity. Okay. Now, any phasor can be resolved into vertical. We have studied in +2 vector algebra. There we have studied that any phasor or any vector can be represented, resolved into 2 components, horizontal and vertical components. Say horizontal component is x and vertical component is y. This is j axis, imaginary axis. So any phasor z can be represented by x plus jy. If we make vector addition, this is y means this is y. So x plus jy will be z as per vector addition. So any AC quantity can be represented by polar form, in polar form, that is r angle theta, magnitude angle theta, and x plus jy, that is real part plus imaginary part. Okay, so this is the actual phasor, which could have a magnitude of r and phase angle of y. Now the same phasor can be resolved into horizontal and vertical components. Horizontal component is x, vertical component is y. So it can also be written as x plus jy. Okay. So here we have studied in this slide, there are 3 forms of representation of AC quantity: polar, rectangular, and exponential form. Exponential form I have skipped intentionally because if you know polar and rectangular form, you can solve AC networks. One is the polar form is represented by its magnitude and angle, whereas rectangular form is represented by real part plus imaginary part. Now let us move to next slide. Okay. Now, how can we make rectangular to polar or polar to rectangular conversion? So first, let us understand how to convert a rectangular form into polar form. Say, this is the phasor Z, which is resolved into a horizontal component, that is X, and in vertical component, that is Y. So if this is Y, this should also be Y. Okay, this is J axis. Now, if magnitude of this Z phasor, if magnitude of this Z phasor is R, so magnitude of Z phasor is R, and this Z phasor is making an angle of phi with reference axis. So applying Pythagoras rule, what can we write? The magnitude, resultant magnitude R equals to under root x square plus y square, and applying for this rectangular triangle, we can write tan phi equals to height, that is y. For this rectangular triangle, height is y and base is x. Okay, so R angle phi is polar form of representation. That means if an AC quantity is represented by x plus iy, x plus iy or x plus jy, then it could be represented converted to polar form, which is having R magnitude and phi phase angle. So what should be the value of magnitude? R equals to under root x square plus y square. So rectangular to polar form conversion, for this, the magnitude will be under root x square plus y square, that is R, and phase angle phi will be tan inverse. It should be altered, tan inverse y by x. Okay, so tan inverse y by x based on this formula. So this is what about rectangular to polar conversion. Now suppose the same phasor Z is represented by its magnitude R and angle phi. Now, as I said, any phasor can be resolved into horizontal and vertical components. So see, this pink color shows horizontal component, which is X, and this phasor is Y. Now same parallel phasor can be drawn here, which is also Y. Now for this rectangular triangle, we can write X by R, that is height by hypotenuse, base by hypotenuse is cos phi. So X equals to R cos phi. Similarly, Y equals to R sin phi. So here it is written X equals to R cos phi, Y equals to R sin phi. So the resultant, the phasor Z is making an angle phi with the reference axis or X axis. So the angle, this angle implies X will be R into cos phi and Y will be R into sin phi. Now what we discussed, rectangular to polar or polar to rectangular conversion. Why this conversion is needed, that will be discussed in this slide. in this slide. See, there are four basic mathematical operation: addition, subtraction, multiplication, division. For addition and subtraction, rectangular form is used. For addition and subtraction, remember, for addition and subtraction, polar form cannot be used. In polar form, this operation, addition, subtraction, cannot be done. So if two quantities are given in polar form, say 2 angle 30 plus 4 angle 60. To make this addition, as it is mentioned, in polar form, addition cannot be performed. That is why what we need to convert these two into rectangular form to make the addition. That is why the conversion from rectangular to polar to rectangular is needed. We discussed in last slide that how to convert polar to rectangular and vice versa. So now I'm telling you why this conversion is needed. In polar form, addition cannot be done or subtraction cannot be done. To add or subtract two quantities represented by polar form, what you need to do is we need to convert that polar form into rectangular form. Then we can perform the addition or subtraction operation. Okay. So similarly, for multiplication and division, polar form is preferred. Multiplication, division, both operations can be done in rectangular form, but it is always preferred to perform such operations in rectangular, in polar form. That is why if two quantities are to be multiplied in rectangular form, first convert them into polar form and then multiply them or divide them. So now let us discuss what are the rules associated with multiplication, division, addition, subtraction, all this. Suppose A equals to A plus JB and B equals to C plus JD. Then what would be A plus B? That is for the addition, as we discussed, rectangular form is used. So these are in rectangular form, these two are in rectangular form. So addition can easily be done. So real part A and real part C will be added together, and imaginary part B and D will be added together. So this implies real parts and imaginary parts differently will be added together. Similarly for subtraction, A minus C plus J into B minus D. Okay. See, A minus JB minus C, it should be plus JD. Okay, so it should be A minus C. If we take plus J common, then minus B plus D. So this should be minus of B plus D. Okay, so there is a printing mistake here. Okay. Now, if two quantities are in polar form that need to be added or subtracted, polar form must be converted to rectangular form, as I discussed earlier. Now, multiplication and division. Suppose for multiplication and division, as I said, polar form is preferred. Suppose A equals to X angle theta, Y equals to B equals to Y angle phi. So for multiplication, what will happen? See, X is magnitude and Y is magnitude. These two for multiplication, these two magnitudes will be multiplied together, and the angles should be added. So A into B will be X and Y, magnitudes will be multiplied, and angles theta and phi will be added. So for multiplication operation, Magnitude parts are multiplied, angle parts are added. Similarly, for division operation, magnitude part will be divided and angle part will be subtracted. Okay. If two quantities are in polar rectangular form that need to be multiplied or divided, it is preferred that rectangular form is converted to polar form. You can perform multiplication division in polar form, rectangular form, but it is preferred to convert them into polar first and then make the division using the rule. Now let us solve one numerical. First, we are asked to add A and B, where A and B are given here. Now, as we are asked to add these two quantities and these two quantities are given in polar form, addition is possible is in rectangular form only. So convert this into rectangular form. So 3 angle 45. Magnitude 3 will be there. And angle 45 will be replaced by this. Cos theta plus j sin theta. So angle will be replaced in rectangular form by cos theta plus j sin theta. Cos 45 plus j sin 45. Okay. So now cos 45 is 1 by root 2. So 3 multiplied by 1 by root 2 is 3 by root 2. Similarly, sin 45, 3 into sin 45 will be 3 by root 2. And there's j. Similarly, b will be, b is 590. Let us assume this as 3. B is 390. So 390 will be cos 90 plus j sin 90. So cos 90 will be 0 and j sin 90 is 1. So j3. So finally a plus b will be, real part will be added 3 by root 2 plus 0, that is 3 by root 2. And imaginary part will be added 3 by root 2 plus 3. Okay. Similarly, for division operation, a by b will be, these two magnitudes will be divided 3 by 5 and angle will be subtracted 45 minus 90. That is this. This is how we can calculate AC quantities. So what is the concluding remark here? AC quantities have magnitude as well as phase angle. Due to having phase angle, calculation becomes a bit complex. AC quantities could be represented in polar form or rectangular form. So for polar form of representation, this is represented by magnitude and phase angle. For rectangular form, it is represented by A plus JB form. This is real part and imaginary part form. Addition, subtraction, multiplication, division of AC quantities could be done in polar form or rectangular form. For addition and subtraction, rectangular form is used. Such operations cannot be done in polar form. So if AC quantities are given in polar form and we are asked to add two quantities, first convert them into rectangular form. So how to convert polar into rectangular or rectangular into polar, that is also discussed. Similarly, if two quantities are in rectangular form and we are asked to divide them, then first convert them into polar form and then perform the division operation. This is how we can perform our operation. So in next class, we'll be solving, discussing about nodal analysis. We'll be solving some numericals or with AC circuit, AC sources, and we'll apply these rules to solve those AC circuits. Then it will be more clear to you why shall we study this topic, how to apply the knowledge acquired in this topic to solve AC networks. That all will be discussed in next class. So as of now, I am ending up here. Meet you in next class. Thank you all.